Time to do some derivatives. You may notice it says derivatives part 1. That's because there's so much derivativing on this test that I needed to break it into 2 videos. Otherwise, it's probably going to be like 47,000 minutes long. So let's go ahead and get started. I've got a preview of all the ideas that are going to be covered in both videos, but we're only going to be looking at this slide for this slide worth of ideas today in this video. First thing, basics, which is what is it, doing derivative of a point, inverses, just derivative functions, things like that, just some basic ideas. Then we're going to do tangent lines and linear approximations. We talk about the mean value theorem and estimating the derivatives. In the next video, we're going to talk about increasing, decreasing, concave up and down, extrema and points of inflection, related rates, and particle motion, which is such a big deal, it's going to have its own video. And it also relates to derivatives and integrals, so it kind of doesn't fit in a derivatives only video anyway. So that's where we'll be. So let's start off with basics. Derivative means instantaneous rate of change. It means slope of the tangent line. We've got our power rule, product rule, quotient rule, chain rule. Got to memorize those trig and those inverse trigs. Derivative natural log of x is 1 over x. Things like that we got to make sure we just know. Differentiability, we kind of already talked about in the limits video just a little bit, but we're differentiable everywhere except cusps, corners, discontinuities, and vertical tangent lines. You cannot differentiate at places where those 4 things happen. Big thing, I've been saying it already, be sure to use the calculator when you have it. Inverses, we've got g prime of y equals 1 over f prime of x, and that's pretty much where we're at for that. Okay, let's look at our first question. We've got the temperature in degrees Fahrenheit of water in a pond is modeled by the function h of t given by all that stuff, where t is the number of days since January 1st, which is t equals 0. What is the instantaneous rate of change of the temperature of the water at the time t equals 90 days? Okay, instantaneous rate of change. This function is horrible. You're on the calculator section on this question. Another big tip, they've got 3 places after the decimal, which is standard rounding in calculus. But you need to find the derivative, and you need to find it at t equals 90. Do not sit there and try to figure out the derivative of that by hand. You will kill yourself. Just go into your calculator, use the derivative at a point feature, and do it that way. I'm going to pause the video because I forgot to grab my calculator, but I'll be back in a second. Okay, so I went and got my calculator, did the thing. One thing, do not forget to have your calculator in radians. We will both cry after the exam if I ask, was your calculator in degrees or radians, and you say degrees. It's going to be a huge, huge thing for us. Other thing, if you have an Inspire, don't forget to have me make it so that it doesn't spit out an answer like 18 cosine of 7 pi over 146 times pi over 365. You're not going to know what that means. But the answer turns out to be 0.153 degrees Fahrenheit per day. Again, just do it in the calculator. Oh wait, we're quiet, we can hear Toby itching himself. Okay, I think that's enough, bud. Cool. So let's move on to our next problem. The table above gives selected values of a differentiable and decreasing function f and its derivative. If g is the inverse of f, what is the value of g prime of 2? Okay, so we're looking for g prime of 2. Remember that previous slide said g prime of y equals 1 over f prime of x. So the y value is 2. What x value gives me a y value of 2? Well, here's the y values. Oh, that says y. Y value of 2 is x value of 1. So we want 1 over f prime of 1, which f prime of 1 is negative 5. So that's 1 over negative 5. Okay, that looks like A. Cool. That's our answer. Didn't even need to know what f and g were. But if you do know what f is, this is a kind of problem where you could sit there and try to find the inverse. Maybe it's a function where you can do that, but it's just so much easier to realize, oh, g prime of 1, that means 1 over f prime of 0. So let's find f prime of x down here. We're going to have to use some chain rule because we've got a function inside of a function. We've got a function being cubed. So I'm going to have 3 times 2x plus 1, quantity squared, times the derivative of the inside, which is 2. So f prime of 0 then is 1 over 2 times 0 is 0 plus 1 squared times 3. I know I just did a lot of simplification in my head and verbally, so let me just show real quick what I did. And that gave me the 6 that I ended up having at the bottom. So that's D, 1 over 6. Okay, this one's talking about the meaning. So the cost in dollars to shred the confidential documents of a company is modeled by C, a differentiable function of the weight of documents in pounds. Of the following, which is the best interpretation of C prime of 500 equals 80? Okay, so 80 is the number of pounds. All right. No, the 500 is the pounds. Hi, I'm Mr. Wiebert. Let's start all of calculus over. Okay, we got C prime of 500 equals 80. C is measured. C is cost. And they didn't give us a variable for it, but let's call it P for pounds. The derivative has units of Y over X. So it's going to be dollars per pound. We're looking for something that says dollars per pound and instantaneous rate of change. So the cost to shred 500 pounds of documents is $80. No. The average cost? No. Increasing the weight of documents by 500 pounds will increase the cost to shred the documents by approximately $80. No, that doesn't say anything about instantaneous rate of change. The cost to shred documents is increasing at a rate of $80 per pound when the weight of the documents is 500 pounds. Perfect. That's exactly what we're looking for. We've got increasing at a rate, dollars per pound when it's 500. That's perfect. That's exactly what we're looking for. Let's do some derivatives. This is a double chain rule. I can see that because I've got a sine function and then I've got an ln and then it's not just an x inside the ln. So I've got a couple rounds to go through. So the derivative of sine I know is cosine. So cosine of ln of 2x. The derivative of ln of 2x is 1 over 2x times 2 because of the 2x that was inside the ln. So this is going to simplify. We've got a 2 here and a 2 here to just cosine of ln of 2x over x, which is b. Okay, this one's kind of, it looks like a limit problem, but that's the limit definition of the derivative they're trying to get you to see, so I included it here. Let f be the piecewise linear function defined above, which of the following statements are true. First, limit as h goes to 0 from the left of f of 3 plus h minus f of 3 over h is equal to 2. Okay, so keep in mind that the function is 2x minus 2 and for values less than 3, and 2x minus 4 for values greater than or equal to 3. I'm going to zoom in so I've got some more room. Okay, so I'm going to do the limit as h goes to 0 from the left for f of 3 plus h. Over h. Let's get that down. Okay, so f of 3 plus h. Let's look again. It's 2x minus 2 when the values are less than 3. Okay, so that means every time I see an x, I need to put 3 plus h. So the limit as h goes to 0 from the left for 2 times 3 plus h minus 2. That's the first bit. Now f of 3, well, f of 3, that's going to come from the bottom because that's where the or equals is from. So we've got 2x minus 4, so that's 2 times 3 is 6 minus 4, so that's going to be minus 2. Over h, that's the limit as h goes to 0 from the left. For distribute the 2, I've got 6 plus 2h minus 2 minus 2. All divided by h. That's 2 plus 2h over h. Well, as h goes to 0, I get 2 over 0. Well, 2 over 0 would be some sort of infinity. So apparently, statement I is not true because the limit is not 2. Okay, so now we're going to go do the limit as h goes to 0 from the right of the same thing. The only thing that's going to change here is instead of using the 2x minus 2, we're going to use the 2x minus 4. So again, I'm going to zoom in so I've got a nice big amount of space. Take the limit as h goes to 0 from the right for f of 3 plus h minus f of 3 over h. That's going to be the limit as h goes to 0 from the right of 2, 3 plus h minus 4 minus 2. Because that was what f of 3 was, minus 2 over h. So that's the limit as h goes to 0 from the right for 6 plus 2h minus 6 over h. Well, look, the 6's cancel, which leaves us with the h's to cancel, so that is 2. Okay, statement 2 is good. The last thing we've got is f prime of 3 equals 2. Well, we can look at this two different ways. Statements I and 2 are the left and right hand derivatives. They disagreed, so f prime can't be 2. Another way we can look at this is if I plug 3 into both of those expressions, 2x minus 2 and 2x minus 4, I get different values. So f can't be continuous at 3, and if it's not continuous, it's not differentiable at 3. So this one's 2 only. This one's a little weird, a little tricky, but there's the gist of it. If y equals x sine of x, then dy dx equals ... Okay, I've got a function times a function here. I see x times sine of x. I have to use product rule. So the derivative of the first is 1 times sine of x plus x, the derivative of sine, is cosine of x. So sine of x plus x cosine of x, that looks like b. Perfect. If f of x equals 7x minus 3 plus ln of x, then f prime of 1 equals... Well, first I got to find f prime of x, right? Derivative of 7x is 7. The derivative of the minus 3, it's a constant, it just disappears. And then the derivative of ln of x is 1 over x. So now I'm going to plug in 1. And that gives me 8. Now I see x cubed minus cosine of x to the 5th. Okay, I've got a function raised to a function. So I've got to use the chain rule. I've got a function inside a function, right? I've got a function raised to some power. So first thing I'm going to do is bring down the 5. X cubed minus cosine of x to the 4th. Okay, there's the derivative of the outside. Now I need to multiply by the derivative of the inside. Well, the derivative of the inside, 3x squared. The derivative of minus cosine is just plus sine. So that looks a lot like answer choice E. Okay, so that's it for the basics of derivatives. Our inverses are just do the derivative or plug something in. So what we're going to do now is we're going to look at tangent lines. They let us make approximations for a function. We didn't harp on this idea too much, but if the function is concave up, so it looks something like this, all the tangent lines are below it, right? So any estimations we make with the tangent line are going to be underestimates. And then if it's concave down, the tangent line's above it, so then we would be overestimating. So that kind of goes counter to our Riemann sums thing. So like I've said before in class, make sure you're drawing these things to justify it to yourself. The point slope form to get the equation of the tangent line, so that the y minus y1 equals mx minus x1. Okay, that x1, they're going to give that to you more than likely. They're going to tell you at x equals this. The slope m, that's the derivative at the x1, and the y value comes from the function. So to get y1, you're going to just plug the x value into the original function. Okay, so let's see what it looks like. The local linear approximation of the function g at x equals 1/2 is y equals 4x plus 1. What is the value of g of 1/2? Plus g prime of 1/2. Well, g of 1/2 I should be able to get by just plugging 1/2 because 1/2 into this line because they made the tangent line at that value. So g of 1/2 is just going to be 4 times 1/2 plus 1 which is 3. G prime of 1/2 should just be the slope of the tangent line at this value. Well, the slope of this line is 4, I can see. So if I add these together, I get 7. So again, this G prime of 1/2 came from this 4 right here, the slope of the tangent line. The function f is defined by f of x equals square root of 25 minus x squared. Part A, find f prime of x. Usually the FRQs don't have questions quite that simple, so we got lucky on this one. I'm going to rewrite this as 25 minus x squared to the power of 1/2. So now I'm going to take the derivative. I'm going to have to use chain rule. It's going to be 1/2 25 minus x squared to the negative 1/2 times negative 2x, which if I rewrite that is going to be negative x over the square root of 25 minus x squared. So that's f prime. Okay, now I want to get the equation for the tangent line at x equals negative 3. So I'm going to do y minus y1 equals m, x minus negative 3 is x plus 3. Okay, to get the slope, I just have to plug it into f prime. So that's negative 3 over square root of 25 minus negative 3 squared is 9. So that's going to be 3 over 4. And if I plug the y1, the 3 into the original function here, then that's just going to give me 4. And there's my tangent line. So I did that maybe a little quickly for at least for y1, but I just plugged negative 3 into f, and that gave me my y1. And you don't have to move anything around. That is an equation for the tangent line. Okay, we're going to look at the mean value theorem, and then we're going to wrap this video up. If a function is continuous on a closed interval and differentiable, the function needs to be continuous on the closed interval and differentiable on the open. Sorry about that. Open interval. Then at some point the derivative and the average rate of change are the same. In math terms, that means f of b minus f of a over b minus a is equal to f prime of c. This is our guarantee the existence of a derivative value. Similar idea to the intermediate value theorem. We're guaranteeing at some point the derivative and the average rate of change are the same. Just like with our intermediate value theorem, we have to say we know the function is continuous and differentiable. That's how we know it. We're also going to show the math work, but we have to show it that way. We have to justify it. First thing, table above gives values of a differentiable function f and its derivatives at selected values of x. If h is the function h of x equals f of 2x, which of the following statements must be true? 1, h is increasing on 2 to 4. Well, if h is increasing, then that would mean that f is increasing. But I don't know what happens in between these x values. They'd like to do this a lot. They like to give you a table of values and trick you with it. But you only know 4 different x values. There are literally an infinite number of x values where so much else could happen. Don't trust things like that. There's no way you could know that. There exists C where 0 less than C less than 4 such that h of C equals 12. Okay, well, that's our intermediate value theorem. I want to show the existence of some h value. So remember, h of x is f of 2x. So I know that the function is continuous because it's differentiable. Now I just need to check h of 4, which is going to be f of 8, based on the definition. H of 4 is equal to f of twice that, which is 13. And then h of 0 is f of twice that, which is still 0, which is 3. Okay, yeah, I buy that. I get 12 at some point on this interval. Last thing, there exists C where 0 is less than C is less than 2 such that h prime of C equals 3. Well, if h prime of C equals 3, that means that f prime sorry, I erased that because I shouldn't have said that. We don't need that. What we need to do is show that h of 2 minus h of 0 over 2 minus 0, we need to show that that is in fact 3. If that's true, then I can say then I can say yes. Well, h of 2 should be f of 4 over 2. F of 4 is 9 minus 3 over 2, which is 6 over 2, which is in fact 3. Sorry, I got a little cramped down there, but it does in fact look like 3 is true, so 2 and 3 only is our answer. So we just needed to show that h of 2, that the average rate of change was 3 on that interval. Okay, function f is continuous on the closed interval. Which of the following additional conditions guarantees that there is a number c in the open interval such that f prime of c equals 0? That sounds like intermediate value theorem, the existence of a derivative value. All we would need is it's differentiable. Okay, A, B, and D are wrong. C, we need it to be differentiable. Okay, last idea, estimating the derivative. You guys are very good at this. If we don't have a function, we have a table value, a set of table values instead. We're just going to estimate the instantaneous rate of change using the average rate of change f of b minus f of a. So we've got Rochelle riding her bike again. We're going to estimate r prime of 4. So we need to find the smallest interval that contains 4. Well, that'd be 3 to 5. So I'm going to do r5 minus r3 over 5 minus 3. That's 112 minus 95 over 5 minus, I guess I can just do that, that's 2, which is 17 over 2. Okay, only thing that we're missing at this point is it says indicate units of measure, so we need to make sure we do that, or else we wouldn't even get the point for all the work we just did. So the units of measure for the derivative, remember that's going to be the units for y divided by the units for x. So we're going to do rotations per minute per minute. And if you don't like that, you could say rotations per minute squared. Okay, that wraps it up for derivatives. Part 1, we'll see you in derivatives part 2.